before we leave today, just as a reminder, I am giving you a homework for the week. This will not be digital on Wayground. You are getting a paper 5 as homework for the week. So that'll be due on Monday. So you have the weekend to work through it. You can't forget that paper 5 exists. So you need to get some practice on it. After we finish paper 4 on May 7th, we will switch gears exclusively for 3 class periods just to go over paper 5. Paper 5 is an analysis paper, so the more practice you get on it, the better. But you can't really predict exactly what's going to show up on that paper, which is why I have heavily suggested earning all the marks you can on paper 4, and then using paper 5 as like your gravy marks for like, you know, a little bit over and above. All right, so let's go ahead and get to Unit 5, starting with polymerization. So there are 2 types of polymerization. We say types of polymers. And what are the 2 types? Condensation's one. What's the other one? Addition. So addition and condensation. Those are the 2 types. This year we went over condensation, but we also learned addition back in AS chemistry, and it can definitely show up again in A. And so what was the requirement for an addition polymerization? Correct, both of you. For requirement for addition, you need to have a carbon-carbon double bond or a pi bond that can be split. So you must have this. And remember, when you do an addition polymerization, you're splitting that double bond and you're writing bonds 2 out. Like where you have the double bond, you're writing 2 out. And so when you have an addition polymer, it's going to look like this. This is the double bond extended out, broken extended out. And then this would be whatever W, X, Y, and Z that you have, whatever the 4 groups are that are connected here, 1, 2, 3, 4, those would be up and down. And then what would we put here? Remember what we would put here? A little N for the repeating unit. That's called addition polymerization. Condensation polymerization, what was that? In condensation polymerization, you form the polymer by removing small molecules. Those small molecules could either be water or it could technically be HX. So the requirement in order for you to be able to have condensation polymerization is you need 2 molecules or 2 groups. The groups can be on the same molecule. That result in the removal of water or HCl. And so what would those groups be? What are the groups we're looking for? So groups could include, we saw 2 of them in the bell work today. We saw amines and we saw carboxylic acids. But it would be amine, alcohol, carboxylic acid, and there's one more that people often forget. Acylfluoride. And basically you need one of these and one of these. They can either be on the same molecule or they can be on different molecules. In the bell work, they were on different molecules. Each molecule had 2 of the same group, but you could have the same molecule polymerize with itself as long as one side of the molecule has one of these groups and one side of the molecule has one of those groups. And you would get a condensation polymerization as a result. And so what would an example of that look like? I'm going to use something I think similar to the bell work, maybe not exactly the same, but similar to the bell work. Let's do it with an acyl fluoride though, because that's a little bit different than what we usually see. So I'm going to do one with the acyl chloride. And then we have this with so how would we make the polymer pair? What would we take out? Take out the H and the Cl from the middle, and then take out a chlorine from here and a H from here, right? So you take one from the inside and one from the outside. And then you have to make everything else together. So this would be the product of the polymerization. Would be this. And how many repeating units is this? One. Because I just used one of each. In the bell work, they asked for 2 repeating units, so to do 2 of each. That's the first topic. What about if you're forming a dipeptide or a tripeptide? Do you remember how to do that? Forming a dipeptide. What would you do for that? Because it's technically the same process. How do we form a dipeptide? Let's say that we had, and I'm just going to use an example, CH3, NH2, COOH plus HNH, CH2, COOH, COOH. How would we form this into a dipeptide is the question. Dipeptide does not mean polymer. Dipeptide means you're only putting 2 together, which means you would take the inside part away. It's still a condensation, so you'd still take out the water, but would you take out the outside part if you're just getting 2? No, just the inside part. So when you're forming dipeptides or tripeptides, you're only taking out the inner waters. You're not taking out the outside groups because you're not making a complete polymer. You're just putting 2 together. So dipeptide means putting 2 amino acids together. So you would get this. And you would get this. And this. And what would the small molecule that removed, what would it be here? Water. And in the one up here, what was the small molecule it removed? HCl. Right? Yes.
Wait, would you need to put that in?
Put the what?
I mean, for the product of polymerization. Like, since it's up in units.
Oh, yeah, you can put the N. Sometimes they do, sometimes they don't. Usually they don't, but you can put that. So I want to bring something up here because it can show up here. It will also show up for any of you taking AS biology next year. Where's the peptide bond?
CN.
It's the CN in the middle. So you should, there's a slight possibility to ask you to point at the peptide bond and write where the peptide bond is, or circle the peptide bond in your molecule. And this right here is the peptide bond. The new bond that's formed between the C and the N after the hydrolysis has been completed. So that was topic 1, which is polymerization. And in polymerization, because it's a condensation reaction, we can also discuss the formation of dipeptides and tripeptides. Tripeptide would be the same idea, to take out 2 waters between 3 amino acids. I'm going to pause, and then we're moving on to our next topic, which is actually more about amino acids, because there's more to discuss. Like we had in the bell work, there was more about amino acids. They used to have more biochemistry in this class. It's been moved out of the class.
Where's the second peptide? Where's the second peptide bond?
There's no second peptide bond. There's two amino acids you're linking together. This is the bond that links those two amino acids together. If you were linking three amino acids together, you would have two peptide bonds. Continue? No, not yet. I'll pause. Good. All right, we're gonna move on. Next section, amino acids. A little bit more about amino acids. I would know the general structure of an amino acid. I would know it on inspection. Typically, they just give you amino acids, but you need to know what you're looking at. And so an amino acid has four groups. It's a carbon in the middle. That carbon in the middle is chiral. Why? There is one amino acid that exists where the R is a hydrogen, and that carbon would not be chiral, but typically amino acids are chiral, most of them. All right, so I want to point out here that this is a basic group. That's a base, that's an amine, it's a base. And COOH is what? Acid. And so amino acids will participate in all types of acid-base reactions. So you could be asked to do an acid-base reaction with an amino acid. But what I really want to discuss is, first of all, the one definition you have to know. Isoelectric point. There's actually a couple more in chromatography that you have to know, but this is the one for amino acids. Isoelectric point is pH at which the Zwitter ion exists. Or the charge of the amino acid is neutral. That's the isoelectric point. And then I wanted to bring up low pH conditions and high pH conditions. So if we have low pH, what would first of all be classified as low pH? We could think about it from the bell word. What's low pH? It's acid, but low pH in comparison to what? Like what's low, what's high? Atzel?
Just lower than the isoelectric point.
Lower than the isoelectric point. So when they say low pH, it means lower than isoelectric. You first have to figure out where is the isoelectric point, and then lower is lower than that. And so low pH means that you're in a H plus rich environment. You have a lot of H plus. So this means that any groups that are carboxylic acids are going to exist as COOH, and any groups that are amines are going to exist as NH3 plus. Does that make sense? They're all going to exist with the extra hydrogens. Yes.
Is it possible that question can just state that the reaction takes place in acidic conditions, or will it always tell us the pH?
I'm trying to, I mean, you have to compare to the isoelectric point because, like in this last question, the pH was 2.8 for the isoelectric point. So if you said acidic conditions, I feel like that would not be clear enough because like 3.5 is still very acidic, but yet higher than the isoelectric point. So I think they need to provide you with that information for this specific type of questions. Low pH, COOH, NH3+. High pH would be higher than the isoelectric point. And this would be a COO minus. And how would my amine exist? NH. And then at the isoelectric point, how would my groups exist? It would be COOH, or sorry, COO minus, because it's got to be the Zwitter ion. NH3 plus. but all other groups, all other side groups would be as they are. They would be unchanged. To keep the overall charge neutral, all side groups must be unchanged. And then while I was here, I have a side note about amides that I think is really important. I said it in the book. I'm going to say it again. Amides are unaffected by pH and uncharged. Meaning amides you do not add hydrogens to, you do not take away hydrogens away from. They are classified as neutral. They stay CO and H2, like that. That's my section on amino acids. There is a little more on amino acids. There's one more topic. It's called electrophoresis. Do you remember electrophoresis? How would that look? You would have like a little thing like this, and then they tell you that you drop the sample somewhere, and then it could be in the middle, it could be closer to one side, but you drop your sample somewhere. A lot of questions, they'll drop it in the middle, but some they'll drop it on one of the sides. And then how do we know how our sample travels for electrophoresis? This is separation based on size and charge. Of amino acids. So the idea is that the negatively charged ions will move towards the positive plate. Positive side as electricity flowing through. Positive ends, better way to say it. Positive ions move toward negative ends. And the greater the charge, the greater the movement. And the greater the size, what happens to the movement? Heavier moves slower, so less movement. And then finally, what if there wasn't a charge at all? Would there be any movement? No charge equals no movement. That was a process called electrophoresis, which is the separation of amino acids based on charge and size. And that takes care of polymerization, amino acids. We're now on to chromatography is the next topic.
Oh, I remember that.
Chromatography. So there's two types of chromatography you are expected to be aware of for this course. The first one's called thin layer chromatography. And so thin layer chromatography, the first thing you need to know for all types of chromatography is there's a stationary phase and there's a mobile phase. The stationary phase is the moving phase. The stationary phase is the phase that's not moving, and the mobile phase is the phase that's moving. And so for thin layer chromatography, your stationary phase is some kind of solid that's on your column. And there's two solids you can remember. One of them is called aluminum oxide, or Al2O3. And the other one is called silicon dioxide, or silica, you can just call it. And I have it still over here. It's like a white pasty thing. And it's like chalky because I can put it onto my thumb. What? So this is what a TLC plate looks like. And so your mobile phase for TLC can be polar or nonpolar. It could be polar or nonpolar. But the important thing is that your solute is going to travel with your mobile phase. And so depending on the difference in polarity of your stationary phase and your mobile phase is how much your solute travels. So your solute, whatever you're checking, travels with the mobile phase. It will travel farther if it's more soluble in the mobile phase. We had a term for that. It's called the RF value. So the RF value gives us just the math that describes this. The RF value is the distance traveled by the solute. And they're usually really easy calculations to do on a Cambridge exam. They'll give you something like this. They'll give you the spot of the dot. They'll give you the spot of like how far the solvent traveled. And then you'll just have to measure, like it's just a division, how much distance is traveled by the solute over how much distance is traveled by the solvent. That's what we call the RF value. So if we had just something like this, the solvent front, and this is the baseline, this distance would be the distance that the solute travels. And this distance would be the distance that the solvent travels, and it's just dividing those two numbers. So what does a small RF value mean? Low solubility in the mobile phase, high solubility in the stationary phase, right? So low RF value means lower solubility in mobile phase or higher solubility in a stationary phase, whatever the stationary phase is. And then what would a high RF value mean then? The opposite, right? High solubility in your mobile phase, like whatever it's traveling with. Bless you. There was another type of chromatography. The other one that Cambridge wants you to be responsible for is gas liquid. And there are other chromatographies that exist. I think right now HPLC is the one that's used the most often, which is high-powered liquid chromatography. It's more expensive, but it gives a way better separation. But these are the two that Cambridge wants you to know. Gas liquid chromatography, which is GLC. If you do end up, any of you take a chemistry major in university, there's whole classes dedicated to the different instruments that are used for techniques of separation. So like they'll go over GLC. There's ion ones. There's Fourier transforms. If those of you who know math know Fourier transforms. There's like a whole bunch of fancy equipment. You get like kind of a preview of it here. So gas liquid chromatography. You need to know the difference in this chromatography is it's not a little tiny plate like you have in TLC. Gas liquid chromatography is a whole big machine that you have a big column that you push your sample through. And so what you need to know about your stationary phase for a gas liquid chromatographer, stationary phase, is that it is some type of non-polar liquid that has a very high boiling point. So nonpolar, liquid, high boiling point. But you may ask yourself, well, how can it be nonpolar and have a high boiling point? You'd have to choose something, maybe like, benzene things that have high molar masses. So you're looking for, high amounts of electrons. If it's going to be nonpolar, it's got to be a larger molecule. That's what I said, like something like a methylbenzene would be a good solvent for a gas liquid chromatographer. So high boiling point, nonpolar liquid. The mobile phase, which is what your sample travels with, is some kind of carrier gas. The carrier gas has to be unreactive. That's why it's called gas liquid, because it's moving with the carrier gas. So carrier gas has to be unreactive. There have been questions where they ask you to shout out possibilities of carrier gases. Nitrogen's a great carrier gas. Any like helium, or you could even choose argon, any type of, relevant noble gas. Don't choose radon for everybody's health and safety. And xenon is slightly reactive. It doesn't really it existed at one point in time, but it doesn't currently exist on planet Earth. Yes.
What does it say next to a nonpolar liquid?
High boiling point. High boiling point. Sorry. So anything like a helium here, argon, etc. Carrier gas has to be unreactive. It's just carrying your sample through. And here you don't have an RF value. Instead, you have something called retention time. Does anybody remember what retention time is?
It's for substance to get out of the
Yeah. It's just the time it takes for the compound to travel through the GLC and be detected. Time taken for sample to travel through the GLC and be detected. And I've run out of space, but there's a little bit more. There was one math formula in here. What do you need?
Next to non-polar liquid, what is it?
High boiling point.
Boiling, making sure.
I'll pause. And we're almost done with the front half of the page.
Can you see the back?
The whole back is carbon and HNMR. The whole back I have is for NMR.
This was the second page.
Yes. This is just the front. We just finished the front. We still got to do NMR, which is like the major thing in the unit is NMR, right? Well, polymerization and then NMR. This usually is a smaller topic on the test, but there's like 3 or 4 marks that you could have. And they're ones that you'll forget if you don't go back and review. Yes. Sophia, can you bring another paper? We lost the rock, paper, scissors. It goes like that. Thank you. Yeah, thanks, Sophia. Thank you, Miss Sophia. All right. Are we good to move on? No? I'll pause for a little while longer.
I've been like a please. Sorry.
No, the unified is
Unit 5 is pink.
too.
You need more pink. You're going to have to staple it at the end. Good now? Continue? Okay. There's one more formula for GLC that I have space on this paper, but apparently not here. The formula for GLC. is they may ask you for the percentage of a substance in a mixture. So the percentage of any compound in the mixture. So in order to get this, all you have to do is find the area of compound A. Whatever compound they're looking for, and divide that by all the areas of all the compounds. What do I mean by that? In your graph, you get this. Compound B, area, compound C. In most questions that I've ever seen, they'll already just tell you what the areas are, and they'll ask you to just do the calculation. However, if they wanted to go one step farther, what could they ask you to do? Like if they wanted to make this the hard question, how could they take this one step farther? It's the area of a triangle. Which means like this is 1/2 base height. So area equals 1/2 base height if they don't give you the numbers.
If they want to go one of them farther, they make sense again.
That's outside of the scope of the course. But
Unfortunately,
if you want to take physical chemistry, that would be that next step. Yes, would be to integrate the areas under the curve, or advanced organic chemistry.
Math reference.
So pure chem majors, yes.
I
would
mean,
do
you're
that.
gonna pay attention, right? And none.
Or-
No less.
They just let the machines do it for them. Typically, like usually the machine has a printout, and then you can just check it to make sure it's right. All right, so that concludes everything that's not NMR. So we took about 35 minutes to do everything that's not NMR. So we've got about 35 minutes to do everything that is NMR. Very exciting. So I'm gonna pause because I'm gonna clear this for a new, I want a whole new screen for NMR. Need a whole new screen for NMR. A whole new brain for NMR. You know. It is, you either get it or you don't type of, like your brain is usually naturally attuned to that type of problem solving, or it's not. If it's not, you have to work a little extra hard to get it. I remember my professor saying, NMR is so hard. It's the most difficult thing you'll ever learn. And I remember looking at it and being like, is that it? Why are they saying it's so hard? But like I said, it is. It's a specific way of thinking. And it's something that has to be developed. But even you can get good at NMR with enough time to practice. Enough time to practice is the thing.
Are you the type who's good at NMR?
All right. Carbon 13 NMR.
Are you good at NMR? Are you?
And H1 NMR. I think as a group we were better at carbon NMR as a group. I mean, and it is the easier type of NMR. So we're going to start with carbon 13 NMR. And so I wrote just basically notes off the top of my head last night on the key differences and similarities between the two NMR. So for carbon 13, this detects unique carbons on a molecule. Detects unique carbons on a molecule. Detects. What do we mean by unique? If there is symmetry, you'll have two carbons or even more that are the exact same as each other, and they would not show up as unique peaks. They would show up in the same peak, right? So it detects unique carbons. carbons in a molecule. In carbon NMR, there is no peak splitting. So that whole idea of neighbors and worrying about that, you don't have that going on with carbon NMR. No peak splitting. Just single peaks. You will always have a solvent peak for CDCl3 because carbon's there. So solvent CDCl3 peak always at 80. Like 80. And it can be ignored. So if you see a peak at 80, that's your solvent CDCl3 peak. The next thing is de-shielded carbons. This is probably the most complicated concept here. De-shielded carbons. This means carbons that do not have the inductive effect of their friends. They're right next to electronegative groups. They're filling the hole of those electronegative groups. So de-shielded carbons next to electronegative groups are always downfield. Meaning they'll be this way. And conversely, shielded carbons, ones that have like a lot of alkanes, a lot of just CH3, CH2s, shielded carbons like bunch of CH2s. Are always upfield, closer to 0. So then for this, I figured the best way to just kind of remind ourselves what we had to do here is I have a couple of examples and I wanted to ask how many unique peaks in each of these examples. So for carbon NMR, how many unique peaks in this? Can you count how many unique peaks you would find on a carbon NMR here? 1, 2, 3. Because 1 and 3 are not the same. 3 has methyl groups on the side, 1 does not. 4. And all the ones on the outside are the same as each other. So this is 5, this is 5, and this is 5. The answer is 5. What about this one? How many unique peaks? And how many unique peaks here? 1, 2, 3, 4, 5, and 6. 6 unique peaks, no symmetry. I would expect the peaks from this carbon and this carbon right here, 5 and 6, to be the most down here. Those would be the ones you would find the most that way because they're the most what we call de-shielded. They've got the electronegative groups right around them. So shielding talks about basically that idea that you have a bunch of carbons that are protecting that group nearby. It's the same idea as the inductive effect, shielding and de-shielding. All right, so that's carbon NMR. So now the big beast of the unit is hydrogen NMR. It's where the most points can be, where the most analysis is, and for many people, it's the most complicated topic, HNMR. So, what does HNMR detect? Unique what? Hydrogen environments. Are the peaks split? Peak is split by neighboring hydrogens. So this peak you have will be split if on the carbon next door there are hydrogens. According to what rule? According to the n+1 rule. Meaning if there's one hydrogen on the next door carbon, the peak will be split into two. If there's two next door hydrogens, the peak will be split into three. So it's the n+1 rule. What about the OH and NH peaks? OH, NH peaks are not split. They show up as what? They are always singlets. What else about the OH, NH peaks? There's more. They disappear when shaken with D2O. So OH, NH peaks disappear when shaken with D2O. Due to what? What is the key wording we have to get in there? Why? Yes.
An even number of, not an even mass number.
Well, yeah, it doesn't show up because of the even mass number, but why does it disappear? It's called proton exchange. So that's the key words you have to get in there. Like it's the D swapping with the H. Due to proton exchange. That's the key there. Very similar. TMS. What's TMS?
Oh, Teenage Mutant Ninja Turtles.
Not quite. Not quite. Not this time. TMS is what? It's your baseline where 0 is set. All other molecules are based off of that. Where 0 is set. So like any number, 1.4, 2.3, 3.5 is relative to 0. 0 being the shift for TMS. That's what we call your standard. The key name for that is your standard. Just like the SHE is your standard for electrochemistry, TMS is your standard for NMR. Anybody wanna, what is the structure of TMS? You know, just in case it were to show up. It's silicon with 4 methyls. Completely non-polar, very low electronegativity difference. That's why they use it. Completely symmetrical. Tetramethylsilane. That's what that's called. Shielding and deshielding works the same way as carbon NMR. So shielding, I don't want to write it again because I have other stuff to write. Deshielding, same as carbon NMR, meaning the more deshielded it is, the more downfield it's going to be. The more shielded it is, the more upfield closer to 0 it's going to be. As I said, if you understand the concept of shielding and deshielding, you actually don't need the numbers. Like I don't usually look at the numbers when I'm solving NMR because you don't absolutely need it if you understand electronegativity. You can reason where things are at. But the numbers will be printed there on paper 4 to help you. This is one of those topics, there's like a 95% chance it shows up on paper 4 NMR. Like out of the topics, this one is almost a guarantee. Not completely, nothing ever is, but very good chance.
5% chance.
That there's NMR on that paper. The next thing is splitting patterns. You have got to know the names of the different splits you could have. So the first one is called singlet. Singlet. What does that mean? There is no splitting, right? Yes, go ahead, Roman.
Just like kind of one group of like just one atom with hydrogens essentially.
I want to put neighbor carbons. That's the official, if they say it. There's no hydrogens on your neighbor carbons. Or it's OH or NH because those also show up as singlets. What does doublet mean? You see a doublet. That means that there are how many hydrogens on your next door carbon? 1 hydrogen on next door carbon or neighbor carbon. 1 hydrogen in total. Yes.
And if there are 2 neighbor carbons or more, they
You have to account for both of them. That's where you likely get multiplets because you have to add numbers of them together. So then triplets would be 2 hydrogens on neighbor carbon. It's always 1 less. Quartet is 3 hydrogens on neighbor carbons. Or quadruplet, if you wish to go that route. They didn't put that in an answer key. And then what is more than 4? You do not have to know quintet, sextet, and septuplet, octuplet, nonaplet, decaplet. Okay, no, you don't have to do that. You should say anything past quartet is a multiplet. Please don't try to impress them in case you're wrong. You just lose the mark. Just write multiplet. Multiplet is more than 3. This is typically when you have hydrogens like this. Like let's say you had this, 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 and then whatever else. This is going to show up as a multiplet. Why? Because there's 6 carbons. I mean 6 hydrogens on the next door carbons because that is a next door carbon and that's a next door carbon. So this would show up as a multiplet, right? That's an example. And then I have a couple more things. I'll pause. I'm almost done. I'm on this little tiny part right here. We finished, or we're gonna finish on time today. I told you unit 4 was definitely the densest of the units in terms of content. This has a little bit less content, but a lot of application, a lot of analysis. We're going to take a look at one more thing, and then I'm going to put up a practice example that's kind of similar to the Bower to see if we're starting to get the point. You'll see right now, so I'm pausing.
Mister, I got a question.
Yes,
What happened to Master Splinter for the TMS?
I know. You're talking about Teenage Mutant Ninja Turtles?
Yeah, listen, that's what TMS stands for, right? You got Donatello, Michelangelo.
You know it's being recorded, right? I'm just throwing that out there. Just throwing that out there. For all intents and purposes. Can we move on? All right. Oh, I need to add another slide. That's great. Okay, so integration. Cambridge doesn't actually use this word integration, but I'm going to tell you from the notes what integration is. So integration, which we know to be something in math called the area under the curve. That's why we do call it integration.
Defined as the Riemann sum between the 2 exponents.
Awesome. And if you were to take physical chemistry, you would then, be responsible for calculating integrations. But all it describes in the purpose of HNMR is how many hydrogens are responsible for the peak. So we saw this in the bell work. How many hydrogens are responsible for the peak itself? It's not how many hydrogens are splitting the peak, but how many hydrogens are creating that peak? How many hydrogens of that type are there? So it's really how many hydrogens of that type are there? Of that environment specifically are there. So I wanted to give you an example So that hopefully it puts it all together. And this will be the last thing that we do is the example. And like I said, we're good on time. Yay. Example. And it will come CH3, C, CH3, CH3, CH2, CH, CH3, C, O, H. First of all, how many unique hydrogen environments do you see? How many? Ramon?
5.
So I'm gonna number them. 1, 2, 3, 4, and 5. There are 5 unique hydrogen environments. So for each one, let's make a table. What is the splitting pattern? And how many hydrogens are responsible for the peak? Okay. So, number 1, what's the environment? Just alkane, right? Number 1 is just CH3, or you can say alkane. The next door environment is pretty much just all carbons. So would we expect the number here to be low or high? Like if I were to look at an NMR, would it be closer to 0 or closer to like 13? What would we expect the number to be?
Like one.
Like 1-ish, right? It should be like 1-ish. What is the splitting pattern here? Singlets. Because these hydrogens are all next to a carbon that has no hydrogens. There is no split on any of the hydrogens in environment 1. How many hydrogens are responsible for the creation of the peak? This is the one that's getting us.
3.
Nope,
Math.
9. Because all of these hydrogens, it's symmetrical here, all of these hydrogens are responsible for the peak. There are 9 hydrogens there, so it should be 9. So if you've got symmetry, you have to include all the hydrogens that are of the same environment. Okay, so that was number 1. We said we have a total of 5 to go through, right? So number 2. This is still CH2 alkane. It should be pretty low. Although I don't think as low because it's starting to get closer to an electronegative group. So it should be a little bit higher in shift than the first one if you were to predict the numbers. What is the splitting pattern for these hydrogens? It's a doublet. It should show up on a graph as a doublet. Because although there are no hydrogens here, there's one right here. And 1 plus 1 is the n+1 rule. It means it's got its original peak, but it gets split by 1 hydrogen. And so it splits into 2. And so this right here would be a doublet. How many hydrogens are responsible for this peak, this environment? How many for this question? 2, right? So that's 2. All right, number 3. Yes.
So I have a question for the CH3.
Mm-hmm.
So do you always choose for the splitting pattern, the one that has the higher number?
Oh, I
Because there's like next to the CH.
think the answer is going to be no. I think that's not right. I think that you have to look at everything that's around the carbon. You look at both next door. So you look right here, this hydrogen right here, that carbon has how many hydrogens? 0. That carbon has how many hydrogens? 1. If they both had hydrogens, you would have to consider both of them. They don't both have hydrogens. You don't consider the one that doesn't have hydrogens. There's no splitting from here, but there's splitting from here. We'll see that when we look at another example. Number 3. Number 3. Okay, so what is this environment? Should be getting closer to an electronegative atom, right? We've still got alkane, but it's got that CO next door. So now it's CH, but CO, or you can say alkyl next to EN, right? What is the splitting pattern of 3 of the hydrogen here? Multiply. Because you've got 2 splits coming from here, 3 splits coming from there. 2 plus 1 is 3, 3 plus 1 is 4. That's at least split 7 times. That's what we call a multiplet. So this is a multiplet, which you would not be able to see past 4 on a graph, so we just call it a multiplet. And then how many hydrogens are responsible for 3? For this one. It's just how many hydrogens are in that environment. 1. 1. 4. This is CH3. It's alkane again. Because it's 2 carbons away from an electronegative group, so you just say it's alkane. Because it's too far away to really say that it's right next to the electronegative group. So it's just alkane again, or CH3. This one right here, number 4. What is its splitting pattern? Doublet. Because it's only got that carbon with that 1 hydrogen. So this is a doublet. And how many hydrogens are responsible for peak 4? 3. It's just how many hydrogens does it have when it says how many are responsible for that peak. And we still got 1 more, 5. This one throws people off, that's why I wanted to include this. 5. That is, that's on an electronegative atom. That's an aldehyde, right? That's true. I would expect this to be way downfield because it's on a carbon that has an electronegative atom. I think that that's going to be way downfield. The most definitely of all of them. How is it splitting pattern? No. That's why I chose this as an example. This is not an OH or NH. Although it's got the oxygen on the carbon, it's not on the hydrogen. You look at the carbon next door to the carbon that has that hydrogen. It has 1 hydrogen. It is a doublet. I knew that would throw us off. That's why I wanted to address that one. This is a doublet. If it had been COOH, it would have been a singlet. Because this O is the one that's blocking. This would have been a singlet. But aldehyde, no, you have to look at what's next door. So it's a doublet, right? And then how many hydrogens are responsible for this P5? 1. Does that make a little bit more sense? NMR is a rough topic, but it's got to be practiced to get better. So I will be giving you more NMR for next class's help and see if we get better at it. And then we'll be practicing organic reactions throughout next class period. Remember I said for the unit 6, 1 pager, you don't really have to make a new 1 pager for that because you've already made the flashcards and made the posters for organics. So I would keep the unit 1 through 5 because unit 6 is all organic reactions. On that note, you can get your workbooks back and you can get your flashcards back because I believe I have graded all of those and they're up in the cabinet 1. So go ahead and feel free to take those back to use and study for your paper 4, which is next week, Thursday, I believe. It's on May 7th.
They are the second.
So we're getting close.
Which is, of course, the day after the mechanical paper.
Yes. I think I am proctoring that, by the way.
Yeah.
So I get to tell you all afterwards, study for chemistry.
We're doing another thing. I was
Wait,
driving around
To relay that to her?
and I remembered it because I saw this.
What's that?
What was the answer for this one?
Aspartic acid?
Yeah.
This one. So it's got to have this H here. This would become NH3+. And then everything else would remain the same. Because it's 2.77 is the isoelectric point. 2 is lower than 2.77. So all groups that could be acids or bases have to be the acid form.
It actually looks good.
So the NH2 has to turn to NH3+. Everything else remains the same.
It's a 7.
All right, let me turn this off.
If you